in CO2 reductions. So we're going to learn all about how to design catalysts efficiently, smartly, intelligently, perhaps, and CO2 reduction and all sorts of cool stuff. We hear a lot about BIDMaP. Thank you all for coming to the BIDMaP seminar. Of course, it's every other Tuesday. We have free food. We really appreciate you coming. And take it away, Mihail.
Thank you very much for the kind introduction. I'm trying to set this up on Zoom, but there's no one on Zoom anyway, so maybe
I mean, both like we're care about the recording more. It's fine. Yeah, I mean, if you just want.
I think I'm sharing, but
okay, it's fine. Just do your best and let the stage go.
Share.
And if I were
is it sharing? No, yeah, I think we're good. Let me see. Screen. Okay. I think we're good. Cool. Awesome. Yeah. Thanks so much for the kind introduction. Um, like was mentioned, my name is Mihail. I'm sure many of you know me. I'm a BIDMaP postdoc, and so I've been working in the Peidong group for the past 4 or 5 months now, maybe 6. I started in July. And so the Peidong group specializes in nanomaterials, and my project in particular is utilizing nanomaterials to design the next generation of electrocatalyst materials for CO2 conversion. And this project is known as the Intelligent Catalysis Discovery Lab, or iCAT for short, if you've ever heard the term. And so today, my goal for the talk is to basically give you an overview of what is iCAT and offer some opportunities to take advantage of the excellent expertise that you all have in machine learning and AI in order to help drive this process. Is many of you work on autonomous labs and stuff, and so I think it's a great way to throw some ideas back and forth. So the overview for the talk is I'll start off with an introduction on what is electrochemical CO2 reduction, why we're interested in it, and specifically what is our unique approach to addressing this problem somewhat differently as compared to other high throughput catalyst discovery efforts. So the iCAT lab consists of 2 thrusts. There's the synthesis of novel materials. So that's one effort, and we're using gas phase synthesis in order to access a unique materials space that is difficult to access through colloidal chemistry, and specifically with the focus on alloy metals and high entropy alloys. Along those lines, since we are trying to access new material space, characterization of new materials is going to be a big challenge, and so I'll also cover some of our efforts towards high throughput characterization, specifically electrochemical characterization using scan probe electrochemical microscopy. And throughout my talk, I'll cover some of, as I mentioned, this is in the very initial stages of the project, and so there's a lot of work to be done, and throughout my talk, I'll cover some of the directions that we're interested in pursuing and opportunities for integrating the expertise available at BIDMaP to achieve this. So hopefully I don't need to motivate the notion that excess CO2 in the atmosphere has negative environmental consequences. And so in terms of addressing that problem, there's two parts to addressing that. One is removing CO2 from the atmosphere, or carbon capture, and Omar Yagi's group and others do phenomenal work on that respect. Then once the CO2 is captured, the next obvious question is, what do we do with it? And so that's where the iCAT Discovery Lab and electrochemical CO2 conversion seeks to make an impact, is basically converting captured CO2 into value-added products, whether that goes into commodity chemicals or whether we develop chemical fuels that can be used in it to develop a closed carbon cycle. Now, my background is in chemical engineering, and so typically industrial processes are driven through thermocatalysis. And so just a detail that is worth mentioning is why are we interested in electrocatalysis as compared to kind of the more mature technologies available, which are based on thermocatalysis. So thermocatalysis typically relies on very high temperatures and pressures in order to achieve chemical reactions. Whereas electrochemistry, you can typically do it on the benchtop in a beaker. So that gives us the opportunity to have higher efficiencies, milder conditions, and also modular systems where we're not reliant on giant plants that are centralized. So in the field of CO2 reduction, there's many, if you look at it, a brief overview, there appears to be many different catalysts for CO2 reduction. However, if we're interested in obtaining multi-carbon products, and on the next slide, I'll tell you a little bit of why we're interested in multi-carbon products. But actually, if we look at that subset of the catalyst space, it's actually very minimal. Essentially, copper is the only known catalyst that is known to make multi-carbon products with any significant Faradaic efficiency. And the reason for that is because it has an optimal binding energy for the various intermediates for the during the carbon reduction reaction. And so I'll show later on that there's a vast distribution of different intermediates, and so balancing those different binding energies becomes very important.
So we're talking about bulk copper, though.
Yes. And so briefly, why we're interested in multi-carbon products is that if we look at the value for multi-carbon products as compared to single carbon products, it's much more valuable to target multi-carbon products, which is why we're interested in this specific subset of the CO2 catalysis. And so as you mentioned, right, bulk copper versus nanostructured copper, it's been known for a long time that copper is a good CO2 reduction catalyst. And so has been known for, since the work of Cory in the 1980s. And if we look at the initial work versus state of the art today, what has changed? Well, what has changed is instead of using a bulk slab of copper, now we're using nanoparticles, and that allows us to create unique structures that improve the activity. So specifically, right, in electrochemistry, your potential is a measure of your driving force. And so if we are able to reduce copper at a lower driving force, right, that's a more active catalyst. So we can improve the activity slightly, we can improve the Faradaic efficiency. However, if we look at the grand scheme of things, right, even although we've made initial progress compared to the theoretical capabilities that we're striving for, we're actually still very far away, and so there's a lot more to be done. And fundamentally, we've kind of through structural engineering, we've essentially maximized the capability from single monometallic catalysts. And so really we need to explore novel materials systems.
What is the theoretical limit here?
That's the reduction potential of CO2, in this case specifically ethylene, which is around.
Is this just from free energy use?
Yeah, just like your reduction potential. Whoopsies. And so there's a vast number of approaches to engineering electrocatalysts. A lot of the work that has been done to date is related to nanostructuring, which can change the activity by increasing the number of active sites. Essentially, we get more reactions per given volume, per given area, and so that increases the activity. However, that has a limitation, and moving forward into really improve the intrinsic activity of materials, we need to explore more advanced, more sophisticated methodologies such as alloying and etc. And specifically why that's a useful strategy is by having alloyed systems, multi-metallic systems, we can begin to affect the electronic structure of the material, and by tuning the electronic structure, we can tune the binding energy of intermediates, which affects the catalyst activity through the Sabatier principle. And so that's known as the electronic effect. On the other hand, having multi-metallic systems creates multiple active sites in the vicinity of the adsorbate, and that also contributes what's known as the geometric effect, where we can have multiple unique binding sites, and so that we're not limited to a single binding energy. And so to illustrate the Sabatier principle is typically illustrated in terms of these volcano plots, where by tuning the adsorption energy of a single intermediate, we can change the activity of the catalyst. The current is a measure of catalyst activity. However, with monometallic systems, there's a limitation in that by changing the electronic structure and tuning the adsorption energy of one intermediate, that affects the other. This is what's known as scaling rate relations, which make it difficult to tune the binding energy of multiple intermediates. Now, this is important because for CO2 reduction, there's a very large distribution of different intermediates because there's a large range of different products. And so we need to be able to have systematic control over multiple binding energies and essentially breaking the scaling relation, which that can be achieved through multi-metallic catalysts, which is where we're headed to.
Wait, doesn't the scaling relations just depend on like the electron band or whatever, right? Like what?
The idea is that I have a slide.
Like it's based on the energies of different bound states, right?
Yep.
So like, how does multi-metallic break?
And so if you have, like, for example, a high-entropy alloy where you have different active sites, then you can have, it's kind of through the geometric effect, right? Where you have different active sites, you can bind the same intermediate in multiple configurations. And so,
All right, so it's at different active sites then.
yes, it's at different active sites, but by having multi-metallic systems, you can kind of tune different active sites in close proximity. So, for example, this is adsorption energy of CO versus formate, and then by having different active sites, right, you can kind of
So
decouple the
The
two.
intermediates have to like migrate between active sites then, right?
Not necessarily. So there's obviously autonomous labs are many groups are exploring this concept of autonomous labs and high throughput synthesis, and there's a standard workflow that I'm sure many of you are familiar with, where typically we start off by screening the literature for potential materials, selecting a subset of materials that we're interested in synthesizing, and et cetera, et cetera. What I want to focus on is the typical route for catalyst synthesis in the literature, which is through solution phase processing. And with solution phase processing, there are certain limitations. Oftentimes, unless you have a really sophisticated instrument, like for example, the Wanda robot at LBNL can do air-free high temperature solid handling, but that's right, a $2 million instrument. It's not quite as accessible for many laboratories. And even with the most sophisticated instrumentation, there are limitations with solution phase synthesis, such as it's particularly difficult to make multi-metallic alloys and high-entropy alloys with colloidal chemistry, because oftentimes there's a variation in the decomposition rates of metal precursors. which make achieving multi-metallic alloys and specifically high-entropy alloys challenging. And if you're not familiar with the field of high-entropy alloys, basically by introducing multiple elements, there's a series of potential advantages. Oftentimes they're kind of grouped together as the cocktail effect. We don't really know what's going on, but it's enhancing the catalysis. Yes.
Can you make sure like the catalysts you're making here are the same each time?
Yeah, I'll cover that later on.
You probably have an ensemble.
Yeah, I'll show a little bit of some of like our preliminary work on the catalyst that we've made, and we're still not into high entropy alloys. We've made like a three component catalyst. So I'll show a little bit of preliminary data on that. But okay, and so then this is kind of how I covered that previously. And so since you bring up the synthesis. So the way we're addressing this challenge is by exploring different synthetic routes. And here we're borrowing from vacuum phase physical chemistry and high vacuum surface science. And specifically, we're using a technique called cluster beam synthesis, which it's analogous to conventional sputtering. Like, for example, if you're making samples for SEM prep where you sputter a metal to deposit a thin film on your surface in order to make it conducting. Similar idea, however, once the elements are sputtered in the gas phase, you introduce a carrier gas that cools the atomic vapor to condense into nanoparticles, and then you can basically deposit a beam of nanoparticles onto your catalyst surface. And since this condensation happens in the vapor phase, it's a physically different process as compared to chemical synthesis, where you're not in colloidal synthesis, your rate of forming nanoparticles is governed by decomposition of your precursors, whereas here it's a physical process that leads to nucleation and particle growth. And so that's the schematic. This is what our instrument looks like in the lab. So we got this installed and running back in late October. And so still very much in the preliminary phases. But the general gist is this is the target. This is where you place the elements that you're interested in sputtering. And essentially, this is the main neutron head. These elements are then sputtered in the nanoparticle condensation zone, where they condense into nanoparticles. And then using the quadrupole mass analyzer, you can actually select a specific size. And so you have very good control over your nanoparticle size. And so that's the synthesis. In order to make this amenable to high throughput experimentation, it's actually the strategy that we take is to use to deposit a catalyst array. So by having a mask that masks different spots on a substrate, we can create an array of catalysts. Because creating a new catalyst material is as simple as just changing currents or potentials during the synthesis, and I'll show you what I mean by that. But the other, so that's one, but the other advantage is that with this strategy, we're limited based on only, whether we can get a 2-inch disc of metal in order to have a sputtering target. And so there's very minimal material limitations. It's essentially, if a metal can be sputtered, then we can use this strategy to explore that species as part of the design space. And so in terms of the characterization, the technique is also very amenable to high throughput characterization, in that we can sputter and deposit nanoparticles on virtually any substrate. So for example, typically when we're measuring a bulk electrochemical performance, we're doing this in what's called H-cell measurements, where we deposit our particles on a carbon paper in order to have high electrode area in order to measure product selectivity using gas chromatography. And so for that, we need high surface area electrodes. And then on the other hand, for structural characterization, things are deposited on TEM grids, and so that you can determine the physical structure of the catalyst in terms of morphology, composition, and etc. And as I mentioned, since there's a quadrupole mass analyzer, we can control the particle size distribution during the synthesis. So as kind of our preliminary experimentation, I want to offer an example of kind of some of the things that we can study. And the first question that we asked as a proof of concept for our system is whether we can sputter a copper molybdenum alloy. And so conventionally, right, copper and molybdenum phase segregate because copper is an FCC metal, molybdenum is a BCC. And so through colloidal chemistry, it's virtually impossible to create an alloy using copper and molybdenum. And then so we were interested whether with this gas phase synthesis, how that would affect that. And so, as I mentioned, creating a new catalyst material is as simple as just changing voltages or currents. And so compared to conventional colloidal chemistry, where the parameters that you're varying are concentrations or temperatures, here the parameters that we're varying are pressures and flow rates. And that obviously has an advantage for autonomous labs because right, changing currents and pressures is very easy to do with the computer. It's also a continuous design space as opposed to right, typically colloidal routes are like a discretized set of parameters. And so it's very, very amenable to that. And also kind of most importantly, we're sputtering a beam of particles, change the current on one of the targets. You know, that's a new catalyst system, right? And it takes 10 minutes to make deposit one sample, right? Depending on how much loading you'd like, but compared to conventional routes where it might take, 1 day to synthesize a new material.
Sorry, what's monomer is just one here?
Yeah, that's like for example, like this would be like less than a monomer because right, this is on steam, yeah. Whereas a lot of times, depending on what catalyst you're using, sometimes you need so that's also like a lot of times particle interactions will affect the catalysis, and for some systems like our copper system, during the catalysis they'll fuse into nanograins, and so having those particle interactions can also affect the catalysis.
Pressure of by the way, is it just air?
It's argon. So argon is the sputtering.
Sputtering, okay.
Sputtering gas.
Gas involved with that.
But you can also introduce, for example, nitrogen if you want to make nitrides, or oxygen if you want to make oxides. And different sputtering gases will kind of affect the nucleation of the atoms. So yeah, it's pretty similar to like making an SEM sample, but it's a higher pressure. Yes.
When you do the sputtering, are you sputtering the 5 samples at the same time, or just sputter?
Yeah, at the same time. So these are the different targets, right? So over here we have 5 targets loaded. And so for example, in the first, right, so for this example I'm interested in like copper moly alloy. And so for example, I'm running current on the copper and current on the aluminum. On the moly here, I'm also using aluminum. Sample 2 is like without aluminum. And so yeah, just by varying the current on the targets, and it's continuous, simultaneous.
So I just have a question that why do you sputtering kind of evaporation?
Yeah, so there's also those kind of instruments. There's many different yeah, there's many different ways to vaporize the metal, whether it's sputtering, whether it's like joule heating. This is just the way the instrument that we ended up going with. This is a so this is like the sidearm, which is a commercial instrument. Then this is our own UHV chamber, and so basically we purchased this. And so it's not home built, and so they're like that we chose because it's commercially available, and it's also I believe more easier to control the sputtering as opposed to like joule heating, right? Because controlling the temperature of the target um as compared to just controlling the current. You don't need to wait for it to heat up, right? You just like press go and the plasma starts. It's a faster throughput. Where were we? Okay. And so yeah, by varying these various parameters, we can access kind of a huge range of different structures. And so there's, I guess, right, the good thing is that we are capable of accessing many structures. It is also a challenge that there is a high sensitivity between the parameters. So, for example, changing pressure slightly, and not just that, but the history of right previous runs can affect subsequent runs, and so there's a lot of cross correlation between various parameters, which gives us the opportunity to make very diverse structures. But on the other hand, it can be challenging, which prevents, a challenge is really an opportunity to incorporate like machine learning to correlate, right, uh, to learn the connection between operating parameters and the desired structure, because it's not a trivial, but you can't go to the textbook and look up, oh, if I run this current, I'm going to get a Janus structure. If I run that current, I'm going to get a core shell. And so that's something that it needs to be uh, studied through a data-driven approach. Pretty long, and it's going to depend on what materials you're using, right? And so in this one, actually, the aluminum kind of segregates to form an aluminum shell. And so that kind of stabilizes the particle. And so you can see that these are metallic phase. So if I go to here, if you look at the electron diffraction pattern, you can see that the copper and the moly are preserved in the metallic phase. And I think that's because there's an aluminum shell which kind of passivates the particle. And that, yeah, the aluminum would be oxidized, but that kind of preserves the core. And so, but to answer your question, right, it's going to depend on what catalyst material you're working with, right? Some materials will be more stable, others will be less stable. And so yeah, to answer the question of whether we're able to form like in alloys, even right, you can see that here we're forming Janus structures, and so there's phase segregation. So even with gas phase synthesis, right, for this particular material space, right, we still observe segregation because of the differences in the crystal structure. And then also, this material happened to not be a good CO2 reduction catalyst, right? The Faraday efficiency for hydrogen is pretty much 100. So it's an interesting proof of concept just to see kind of the capabilities. However, that's just one example, yes.
So for every set of metals you choose, you'd have to sort of search for the conditions that help you get your nanoparticle.
They always produce nanoparticles. Well, not always, but they will oftentimes produce nanoparticles. But for example, you can produce like a Janus structure or a core shell structure, right? Like the parameters will affect.
They will have a different set of metals, the same conditions one.
Yeah, exactly.
But then that's a search.
exactly. And so, for example, here you can see this is the current through the mass spec. So this is essentially the particle yield rate or your deposition rate. And so you can see going moly versus copper under the same conditions, right? You have very different deposition rates. And so that is where kind of employing machine learning to develop a model that can relate the parameters to the desired structure is something to pursue in future work. So yeah, high sensitivity to experimental parameters and complex correlations between them, which is good because we can access a diverse set of structures, but it's also challenging to control, and so opportunities for the expertise of everyone here. So then I'll shift gears a little bit to cover the characterization. And so, right, previously I was talking about synthesis. Now, let's say we've made our catalyst array. We still haven't been started making catalyst arrays because this is still under development. But and so that part is still under development, but the instrumentations to actually do this we installed in December, and so this is beginning to be operation. But anyway, I digress. The point being is our approach to high throughput experimentation is to basically make localized electrochemical measurements, and the way we do that is with scan probe microscopy. And so similar to AFM or STM, right, it consists of a controller to move a probe and then an instrument to measure signals in that probe. In our case, we're measuring currents and potentials. And we can do this several different ways using related techniques. So we can have a pipette, which creates a meniscus at the substrate electrode, and essentially this is localizing the electrochemical cell. Whoops. And so we can jump around to different points in the array, measure the activity. We can also use what's called an ultramicroelectrode to collect reaction products in order to get an estimate of Faradaic efficiency, or other words, selectivity, which of course electrochemical detection is not doesn't have the specificity of gas chromatography, for example, but it's a good proxy. Did I double? Yeah. So anyway, this is our instrument that we set up in December now, so fairly recently. This is the SECCM platform, where we have our environmental chamber flowing CO2. And then our preliminary experiments are on copper TM grids, where we have a homogeneous catalyst, right? It's not a catalyst array, it's just a single material. So we'll move on to arrays in the future, but as a proof of concept, doing this on a TM grid, which also allows us to do a one-to-one correlation between the electrochemical activity and the catalyst structure, because we can do our SECCM experimentation, take the grid to the TM, and then get catalyst structure. And to give you some perspective of kind of the resolution and the size, or like the experiment, this is an SEM image of the probe, and so you can see kind of the size of the electrochemical cell is on the order of a few hundred nanometers. This is what's called a pull-up curve. So basically, after the pipette has approached the surface, as we retract the pipette, you can see the current drop once the meniscus no longer contacts the surface, and so from there you can estimate like the size of the electrochemical cell. And so to put it into perspective, if this is our substrate electrode with our catalyst deposit on it, right, we're measuring maybe like a couple hundred particles at a time. And so in this our initial work, here we're measuring the catalyst activity, and so on this TEM grid. And so, for example, heterogeneity in the substrate can affect our observed the observed signal through catalyst support interactions, as simple as whether the TM grid bar is more conductive substrate than the carbon support. But importantly, if you recall from in electrochemistry, your potential is a measure of your driving force, and then your current is a measure of your rate of reaction. So the way we assess whether a catalyst is more active or less active is, we can choose a certain potential and look at the current, or we can choose a certain current and see what the potential is. And so, for example, this plot, I'm plotting the observed the CO2 reduction current at a single potential, which is an okay measure of activity, but it's not really the best descriptor of catalysis, right? We're essentially using 1 point in our data, right? There might be 1,000 points in the CV. We're throwing out 99% of our data, and so opportunities for integrating machine learning into this workflow is, for example, doing a classification on these CVs in order to maybe group these by specific areas in order to identify our areas on our catalyst array, right? We don't have to go, if we have a catalyst array with 100 different materials, right? Do classification to identify groupings, and also how to extract good activity descriptors from this data set and utilize the full polarization curve. And
what's preventing you from doing the full curve? Like in usually a CBC scan the voltage, right?
Yeah, and so we have all that data, but then the question is, how do we process it efficiently? Right, because if I want to, right, this is like 10 gigabytes of data. I can go through 100 different CVs and look at them by eye, but that's slow. If I just plot all the data, in like a two-dimensional plot, right, I have to choose one point in order to do, because it's a three-dimensional data set essentially.
Yes,
and so I can give an example of how this problem has been approached in the field of corrosion research. So in corrosion research, the experimentation is kind of similar. It's also uses scanning electrochemical cell microscopy. However, instead of measuring catalysis, we're measuring corrosion by, as you increase the driving force effect, you begin to oxidize the surface, which is known as corrosion, and then your current goes up. And so in this case, again, it's kind of the same problem of how do we have 100 different CVs. We're interested in an activity descriptor. In this case, it's the pitting potential. And so here, the pitting potential is defined as like the transition between passivation and activity, which you can do linear fitting. However, right, for more complex voltammograms, ones that don't fit into like a more idealized profile, you can this work develops a neural network in order that's trained on these good polarization curves in order to estimate the fitting corrosion of these. And so that's kind of a way to give us a single point activity descriptor out of the CV, so that we can, for example, may make a plot of activity that's a better descriptor of activity. So anyway, hopefully you found that interesting, and some good opportunities for integrating machine learning and other ideas. I mean, not just that, a lot of you work on autonomous labs and similar concepts in general, and so I'd be happy to hear your thoughts. And then with that, I'd like to thank Professor Peidong and Professor Bingqing for as my advisors, and then Maria, Julian, Andrew, and Yasin in the electrocatalysis subgroup and the Peidong group in general, and all of y'all. Thank you.
Questions? All right, awesome, Michelle. What about temperature control in the synthesis, right? I mean, because you have the phase separation. I mean, have you thought about just like rapidly cooling it so it doesn't do that, or?
Yeah, exactly. So temperature so like in order to do promote condensation, aggregation of the particles in this jacket, this is cooled with flowing water, or you can run like liquid nitrogen. And so that's That's the cooling over here. But of course, the cooling in the jacket is going to be very different than like the gas temperature. And so that's where there's not a good way to measure, right, the actual gas temperature. That's where you would need to develop some kind of a model that relates the currents, the current on the targets, the flow rate maybe in the jacket or the temperature of the jacket to the actual plasma conditions.
Yeah, I mean, do you have a sense of whether the Janus structure, they're called Janus structure, whether these form in the like gas phase or when they're on the surface?
Oh, that's a good question.
Yeah, it's like what if you like rapidly pull the surface like with that? Yeah.
We so this thing that we're getting this sample stage, it will have heating and cooling capability. Probably not a huge temperature range. I mean, a lot of times for solid state synthesis, right? Doing this in like a tube furnace, you're changing the pressure to hundreds of degrees centigrade, thousands. So I don't know if the temperature will be high enough to actually affect to enable like atomic diffusion. But one thing that you can control is the bias. And so there's for soft landing or hard landing, if you're familiar kind of with the this field. So basically if you because the particles are charged, you can apply a bias to the substrate and you can smash them at high energy, several kV of energy. And so that's kind of where you can control the structure secondarily by the impact energy when you're depositing them.
Yeah. I'm just asking, like, there might be a lot of stuff happening between the time you deposit them on there and the time you look at them, right? So
yeah,
it's worth considering.
Yeah,
that's cool.
I might have missed this from the CV plot, but how do the durabilities of these high-entropy catalysts compare to the copper, like the copper nanoparticles?
Yeah, exactly. I mean, we haven't begun to address durability yet. That's like essentially a secondary uh, question, right? First, we want to identify an active catalyst, then we can look at durability because typically in order to do durability, you just need to run it for a long time. I mean, people come up with all kinds of accelerated durability tests, but the real measure of durability is how long it actually runs. And so if you want to actually measure legit durability, you need to do long-term experiments. And so then it's not going to be high throughput. That's they're kind of mutually exclusive. And so the strategy is to first identify promising materials and then look at durability. Good question.
But the core shell structures, are you creating them by like activating all the materials, I guess the metals you'd want in it at once, or are you like doing the core materials first and then the shell comes afterwards?
All at once.
All at once. Then
So-
you just kind of tend to I don't know, like,
Phase segregate.
yeah, face it, yeah, exactly.
Yeah, so I mean, the you can buy an installation, like you can have a sputtering head on the side. And so you sputter particles and then like sputter them a second time to intentionally make core shell structures. However, I mean, if you think about like a catalysis, like in order to have like strain from the core affecting like the binding energy of the shell, right? Strain will dissipate within a few nanometers, right? And so if you have a shell that's thicker than 1 or 2 nanometers, it's essentially like having a bulk material. And so a lot of these secondary sputtering sources will make a core shell structure, but that shell is 5 nanometers large, and it's not going to affect, right? The core and the shell are essentially decoupled.
So once you've have everything assembled the way you picturing it with making the arrays, what's the rate limiting step in your workflow? Like what takes the longest time, and what rate of like how many catalysts can you characterize per day, let's say, something like that?
I think the rate limiting step is always the errors that come, right? If everything's running smoothly, right, it's one thing, but then there's always something that goes down. And so realistically, that's the rate limiting. It's like the most whatever is the most reliable system, or like the least reliable system, is generally the rate limiting step. If everything's running super smoothly, I don't have the intuition for it. I mean, for example, sputtering an array of 30 catalysts, let's say it takes 10, 15, 20 minutes per catalyst to sputter, and you make 100. You can do the time, it'll take, a day, right? Let's say a day. Or if you automate it, you can have it running overnight. The SECCM, so scanning the array with this guy, that'll also take, overnight. And so both of those are probably like an overnight process to make one catalyst array, and then to scan it with the SECCM. Structural characterization, that's going to be the rate limiting step. If you want to take every single thing to the TM, that's definitely the rate limiting step.
But then you could maybe like wait for your SSM results first, and then
Exactly. Yeah.
Cool. All right. Well,
Oh, he's got
sorry.
it.
I can go ahead.
Here.
So in your model system, the polarization curves, you show like two locations are not really like homogeneous in activity. So when you eventually start to make catalyst arrays, how do you screen for like data quality if even the model system does not behave the same way?
Well, this is because it's a TM grid, so you have like grid bars and then carbon. So for making the array, it would be just on glassy carbon. And so it'd be so this is heterogeneous, not because the catalyst deposition is heterogeneous, but because the substrate is heterogeneous. And so if we use just like a glassy carbon disk, then there will be less variations. Now I'm sure there will still be like variations, and so that's where kind of integrating the machine learning to do classification of CVs, so you can kind of say, okay, this is like one series of data. This is another. I can extract the activity from this space. I can extract the activity from this space, and how then looking if there is a difference, like a spatial variation that's not due to variation in the deposition, but variation in the substrate, then that's something we can study afterwards if we know kind of what that distribution is like.
Do you kind of expect there will be a signature in the polarization curves that indicate that?
Yes, and also I didn't show, but we also do EIS, and the EIS is more sensitive to variations in like conductivity or the capacitance.
All right, so let's all thank Mihail for this day. And thank you all for coming.
Thank you.
We'll have another seminar in 2 weeks. So thank you. Really, really nice.
Oh, thank you. Yeah, hopefully it was what the in the spirit of the seminar.
Oh, yeah, for sure. I mean, you're actually part of it, and so the most relevant of it. I mean,
Well, because like the
questions.
spirit of the seminar is to bring in other people.
Oh no, it's something. Like I actually think we should probably do something like this. Like
I think it
A
is
year,
for
yeah.
people to have an opportunity to share what they're doing.
it's like 7 months into your postdoc. Like, what are you doing at BIDMaP? That thing. Yeah.
Yeah. Let me grab some lunch and then we can chat. Yeah.
Guess first. What do you got first? You want to try now or later? Okay.
Not least, yes, let's.
I know you did just
Especially because Apex proposal is really interesting. And I found one other opportunity at Yeah, which is also some. What do you think? Says the mammal scale yeah, definitely it's crowded. Yeah, and I saw that the deadline is on March 6th, so it'd be like we have some time to water it. And I'm planning to right? Yeah. So I think I was trying to write a project and I didn't know what I was going to write. I don't know if I was going to write how you got started if you have any yet. I think I need to figure out what is that or so I guess one of the main ideas is that we need a good way to get so it's going to phase theoretical phase diagrams and then as a functional side. Yeah. Well, so basically, one thing that we alluded to is like when you think about what philosophy activity, obviously it's like surface sites. Surface sites.
I guess 2 weeks ago, and then that's what we got then.
We will in some ways so for example,
There was only like
if you want
theories or something.
like it depends on what you want. Like if you think that it's easier, it'll pass the
You gotta
but I mean, it's because the device doesn't mean that many of us
I will say like it took the time. It took a paper's research time to like do it properly. Like I just
consider a small
thanks. Yes, there was like 25% less transitions extract, and then a lot of people didn't get around positions. Yeah, they really don't know. So even with the interviews, something they can learn. You see, request response. I don't know. They don't know. Yeah, but I'll do 6 years. Yeah.
obviously all the reactions.
And Montana, they really.
So we really need a way to
No, but then some places will observe that they reverse that.
It's like watching the Olympics where you see some
We also
I think
crazy.
most schools though are just saying
This goes over.
that's what we have. So yeah, I think that's always a question. It's like that's like it's really fun, like stuff like have you it's like have you ever tried to over South Carolina? I was like well in America they ask you like always you know there's like your so like 5 people just share well, it's probably like some like civil war shit that carried over until now. So hopefully,
Yeah, but what I'm thinking is
South. Perhaps not yet. Type out other. Not yet.
We still are like just like building.
If I do this,
Yeah, that's what we're working on. Trying to get this.
So they do.
No, so because we haven't like explored it. Like we don't.
Yeah, no, I don't think it does.
Gas environment set up, whereas now.
These are all. So it's like that's the other part was so I didn't hear back training, so it's not hear back. And then she learned so it's tolerating. So I heard back from Notable, but they said like that great.
You can talk to.
I think the only one I
Good.
Proceeding or if they never be.
Try to say like.
That I asked you guys about that. It was still bad. I don't know how I got this. They were like, she looks effort to it's like, yeah, if you want to okay, let's say one there, it's like obviously they want, yeah, I found out like my law system. You found actually it's a high activation energy to like get everything started, but then once you start that process a lot very efficiently saved. It's like you can't. I just and then that's not all the things I only have one of my three. Who's my hands in Miami and I want to do like EM grid or like class and then just use like that side and that's going to be. This doesn't fit the robot's fingers because it can't. For chemistry, there's this it's just the yeah, it's just this is
Okay, I understand that it's like.
Sample state, I mean, like, it should be.
Like I can send you an example, but I saw one example of on our website, but it's almost. Yeah, Laurie is.
Which is really.
So very. And
It's really funny, like so like failed or something that they don't point right.
yeah, exactly. That's
So you're depositing
like
the
direct.
I know it's not.
That one.
put it on this phone,
I guess it's like a
Because that's like what the
I'm sure.
right? Yeah, we don't.
Yeah, I think you definitely have it.
Oh no, I guess they failed their search, but now it's very close. It's pretty close to someone.
It also needs to be like in a high tech, whatever.
Anyway, so it's just a yellow, right? It's not so. And it's blue.
For example, we were bringing out like 6 samples. We have the carousel. So we have 6 samples.
Okay. So maybe just like, I'm just kind of like I'm learn a little bit more. Sort of. Because other than and so it would be helpful to someone so that we can try to.
Most places.
Types of
So it's like you.
proposals kind of for the side one because it's really not there to.
That's kind of what that was.
Yeah, but then, yeah, but in when it's like.
Yeah, so like those nice empty graph with different parts, right? Versus time, there was like
Also need to
3 samples.
acknowledge
Those are
their
different
resources are important for them.
And then you can set
Like, if you
stats.
However, if one was hired, I don't even know some of those figures. How we going to talk?
Again, I mean, just put it, the SWC is like 10 centimeter. Let's say I'm depositing another glycine carbon, I can put
Yeah, so like. The
six pieces of glycine carbon next to each other. Yeah.
Yeah, stuff. Sure, back. And then see how you get.
I did have practice, because I like practicing this in the morning.
Oh, yeah, it's really tough. But I mean, what was to me, like. I only. I did all these human reviews and I did get. I ran it out. Like that is so bad. Yeah. Yeah, we'll see. Yeah, obviously, but like any of them. I think it would be. Hope I'm holding out hope for this. Yeah. Like, great food. Yeah, it's like in my stuff, it's AI for quantum chemistry and molecular quantum chemistry. It's just like exactly myself. But if I don't get that one, guys, do like that one, but no, I think I fucked up. Like I made a small or something. I think I should have just saved chemistry. I'd say ask for references, but I mean, if I'm honest, though, I could try to look at rank other conditions, but I have some of those very strong with the action of those about it's like and provides the place, the only place something like that's really.
I see a lot of,
I mean, I made the argument.
right, every paper is using machine learning.
Both say that.
I see very few like effective, where I'm like, oh wow, this makes a
But like,
difference.
yeah,
Like the machine learning and atomic potential,
next
for accelerated DFT, like that's a big,
no,
like significant advancement.
I think I
Otherwise,
yeah, but like
There's some,
but Ken is like, I think they're we're hearing that DMT's bad, like, it's like, if you're not like to accept that DMT's bad, like, they just. Laura got Vanderbilt. Yeah, and then I feel like she get that. I'll be able to. And then there's a post like I know not having to play around forever. Was there a crew who does lasers? So he has like.
and some places on the get it.
Well, the thing is, he had like I don't test last year. Didn't get. Yeah, no, that's which can happen.
Concrete, like,
Yeah. I know, yeah, so I think he does 6 months like here this year, one month this day after two, so like he is hopefully definitely gonna go to the. Yeah, well, again, like you're kind of happy. You can't be chosen. Like if you listen to the. Yeah, the thing is, like even in Berkeley professors, like you ask them,
The problem is,
they're almost
automating
almost like I applied to 20 places.
data processors, like 40 studies, and then automating like identifying
Table spies, yeah.
the crystal structure with the
Right, I mean, also just like it's just like lasers are.
So you just take your data set and then you look at it, like, oh, this is what my material is.
It's like it's
Like I spent a week trying to like
get it.
Yeah. integrating the intensity profile, oh, this is the spacing, oh, this is the crystal structure, oh, it's got looks like this, oh, it kind of looks like that.
So that
It'd be, create a model that has a, just like spits out a list of structures and like the probability of it being that structure. It's like 98% copper, metal, or.
Yeah, you guys know it's there. I'm playing around a little bit.
Yeah.
I've actually tried to reprocess some data.
No, I think
more than a year ago.
Jacob.
Yeah, passage like try back then I processed it with the UI. I think so. It's just more beautiful. And there's like I'm sure you have seen like from the videos and they have those tutorials where they walk you through their data, but then. Just what I carry, but it's crap. Yeah, well, generate the vacuum probe, so it's supposed to be this out like your beam. Like inverse, like that is, like, it's not surprised, like 50 or 60, like, those are things that's very. You know, is it this guy? Or Gary, sorry, Gary, he's still. Sorry, I'm sorry, Gary, you're dead.
I know like Peter Hirsch.
Okay.
Also, some animation. I don't know if
Like
like on
researching just included, yeah, okay.
Karen does.
I think most of them are very with this guy was so I'm so sorry. I was looking at Yale, I was like, oh, I know this guy. He must be Yale. No, and then, you know, see this guy I'm gonna talk to. He's actually. Yeah, I understand you're the person I'm reaching with in this. I used to work with no, I'll be in like 3 weeks. Yeah. No. It's Charles. Okay, this is my honest weakness. Is like I'm really bad on trying to stop. Yeah. So this guy. No,
There's definitely an advantage for it with assistant professor and then
like
the pace. You're gonna get a lot more mentorship. You're gonna get a lot of your paper published.
Like the downside probably is, yeah, it's gonna be Austria is more work probably also to do a little bit more that part of your yeah, and then she got to Berkeley to sun your hair, so like she was good like her research for that. If you get along with the first time it was like so yeah, it's interesting. Yeah, it's like not I think it's really slim field because they're honestly worse there than that first.
Yeah, like
Really hard and then
he got tenure like after I left. And so
Yeah.
at first it was like that.
Like yeah, so Bingqing,
You know, I was an undergrad, so not as much
process
it wasn't as like hands on like and not as high expectations for it. But still like much more than a Bruni or a beta.
I think that Orgo this is really bad, like getting to my details experience where it's transitioning to like
I agree. Yeah, but even the reverse order I think is better than never having done either. Because if you do become faculty, like you're gonna start off as assistant professor, you know. It's good to see how the sausages move.
so crazy as some obituary.
Peidong makes it look so easy, right? You think, oh yeah, easy, I can do that, right?
Yeah,
You start a group of five, right? That's right.
The only thing that is so very that's good for get talk there is. And this is site this hard.
What do you think is that it's going to serve and goes to you because
That is really fun because most people aren't really experts in your field, like most people, they're like, you know, they listen to the talk, they're like, oh yeah, that's cool, that doesn't ring. A lot of your reputation you build like that, it's, you know, a handful of people, there's like 7 people in the whole world that actually understand what you're doing. Everyone else is like, oh yeah, that's okay, cool. So you're doing like a good time. Flashy copy.
you should be fine. I'm talking about clients instead of being quiet. It's like, it's like,
Like the
yeah.
They couldn't share about it.
It probably everything's.
Yeah.
That's what you're shooting for.
Yeah, exactly, like, what's the point? What is it? I mean, it's really like motivating. You're just like, oh, you know, around these, 17 conditions and, permanent labs parameters, and then, 5 significant failures, like, here, there. The question is, what does that really tell us from less than significant?
Let's see. The search used to first of so like 4 weeks and the next day was
Yeah, I think.
So you get like a response after 4 weeks?
think actually first that's it all and I'm after it like several weeks later and then she'll like so I figure out perfect time of the day to charge, which probably too early to her. I think they don't always like sense of all this was like 5:45 a.m.
Yeah, y'all told me to email her around like 17. Anytime you fucking start on our stuff.
I also reached out to was directly completely so I said, set an appointment with teacher staff while y'all got their crowd.
That's good. Yeah, I think I know that guy. Would you do a postdoc?
Yeah. I think a lot. And firstly, I think already learned a lot from him. I think he is learning at a faster pace than I am, so he has new things to teach me, but still sort of like along the direction. Secondly, just pretty intense now that I'm fighting for tenure basically. That's too much pressure to me. He's very good to work with it and it's not with that very fast.
I suspect that's good. Did he tell you about his postdoc Sunbeam or something like that?
He did somebody on like I was that's all perfect, right? In and out fast.
We burned him hard.
You gotta stay on the friendly side.
Yeah, I was a great friend to have. Terrible guy. Yeah. I know, like Scala was telling me that, like, they shunned his whole group. Like Skylar and like the Muller group, like people in the Muller group will not work with like anyone in that group.
And previous negative experience, so
Well, Skylar was telling me that, like, for example, like when he was doing the experiments at Prof, he would like tell Skylar, hey, align the microscope for me, I'm gonna, so I can do my session. Then he like didn't like acknowledge him on the paper and like stuff like that, or like he wanted to take the tychography, like right, like so Skylar and like people who are developing tychography and stuff. Yeah, once Skylar did just like train his students on tychography. Definitely. And look, very like Yao has been very supportive for me, so I'm like, very like, enormous amount of gratitude for him. Don't get me wrong with that. There's like heard lots of stories from other people that have worked with you. Like, I mean, when I was in a Bridges group, it was like a first year, second year, like half the people didn't talk to you.
yeah. it's a lot. Same for me. Like my first paper is like all just doing basically. Like he could have supported anyone to do like right. I was like my Jack's communication basically just like some analysis, right? He collected the data, we have made the article, and because he was like he was my mentor basically. He pushed me to do the analysis right at the paper, but he could just as well support my readers hang out together. Yes. Actually, he wasn't very happy about that.
Has she ever mentioned it?
No. But I can't imagine the whole time. So
Yeah, and also he's like nice. He's like especially harsh to like Chinese. Like most of his enemies are like Chinese people. And for example, his postdoc Sunny, like what Yao told me, it's like well, most of his people in his group, you know, like Yao told me that he felt how did he phrase it? Like, felt offended that his fellow countryman was not performing. He's like, or his fellow countryman because he expects he expects a higher standard for it.
this German guy, I'm glad he didn't even show us that work at all.
I think he valued, like, he really values friendship. Like, yeah. And so he does foresee that.
That's not even my last.
Yeah, I think he.
Yeah. What's the difference? First of all,
Yeah. I'm going to maintain your friendship and that's what post. But I think even like his PhD students, but like I don't think he's especially harsh to his postdocs. But he does like balancing again. It's kind of like the if everyone decides I will support this person and he supports this person. He decides I will like use this person and he uses this person. It's it is very much just like look at the draw. But like for example, at the very start, he said like, when he was first starting his life, he pretty much told me I will support Valentine for until he gets a faculty offer. I'm gonna burn somebody. Yeah. He's like, I got two Korean postdocs. They're on like a fellowship, it's like a national fellowship. They get paid like 50K per year. And they asked them if yeah, well, like, and they have like a family, you know, like I think one of them. He's definitely married. I don't know if he has kids or not, but you know, he's like supporting his family. He's like, yeah, can like you raise my salary to like be a regular to like match postdoc salary. Yeah, like but he's happy with like those guys that you renewed their contract. Yeah.
I think for you like kept, so I think they would like say all the GCs on the lab. You probably know was super experienced with their talking to the dog too, but that's just pretty harsh. Case something, I think that the this group has already tried everything and more than I know. Like just trust him on this. Really hard. At least one of these story. 然后现在所以那些电影的要求，现在到很多人有那些的这个方式，这个
I talked with him at the JRC. I don't think he's on the market this season.
Oh. I would just think that, like, the told me that there's the sign that related to the revisions of the repeated, like, this communications. Could mean many things.
Maybe I asked him about the US. Maybe he's applying to here, I'm not sure. But he's nice. And he's has a lot of expertise in his area, the single crystal. Although now I'm kind of tired. No, myself.